Okay, all right. Okay, all right. First, test is out of 41. If you would like to take a retake, you don't need to tell me right now. You can tell me by email, come in after school, before school. Just come in, spend 5 minutes with me. We'll go through the problems you missed. Retakes have to be done. Shh. Retakes have to be done by Thursday. So you have short notice. The reason why is I need to get them graded for Friday. All my stuff's due on Friday. So, yep. So now, if you're going to retake it, some point this week, come in and talk to me. You can even email me, just say you're going to come in. I require that minimum now. Sorry, this is a copy. The copy is totally blurry. Sorry, I left my copy at home. Luckily, I had scanned it to my computer, so I printed it, and I rescanned it again. It got even worse as it went. All right, so now, okay, all right. It is cosine. Cosine is a little U shape. So you automatically missed a point if you didn't draw the right U shape. Second one, you had to find the starting point. The starting point is negative pi over 2. Or sorry, negative 2 pi, I should say. Negative 2 pi. Then you're gonna be adding pi over 2 each time to get to your final answer. Now, because how I got that spacing, on normal cosine, you go 2 pi, cut it in half, so the spacing is pi over 2. That's how I added it every time. Then your height, if you're starting at 3, you're gonna go up 6 and down 6 from there, because you've been shifted up 3. That's pretty much what I need to see. Some people did some really nice work. Just make sure you're showing all the steps that you need to. Okay, now, I had some people, they did a really nice job of like simplifying these all down, because this one actually ends up being 0 in the back here, which is fine. I didn't require that you simplified it. Some people did, that's great, but you didn't need to. Now, let's go to number 2. Okay, so now, number 2, this is a cosecant graph. It is based on cosine. You can actually see my cosine graph very faded. Okay, so then, what I do is I've shifted this thing over 5 halves, because that was the starting point. The spacing, normally sine goes out to 2 pi, but since there's a number in front of x, I divided it by 2, so it's pi. Cut it in half again, so my spacing is pi over 4s. So you add pi over 4s every time. So you just do the normal spacing.
Wait, wouldn't it be pi over 8?
No, it's pi over 4, because it would have been, pi was the 4th marker, you cut it in half again. Now, I've been shifting down 4. You went up half, down half. I think the goofiest answer I saw, somebody had these numbers flipped. Okay, that was the goofiest answer I saw. Now, okay, when you draw a cosecant, you have to go the opposite of sine. Sine's going up and down, that type of thing. So you have to, cosecant goes the opposite directions from that. So this is the normal sine graph. So then I just go the opposite directions. Okay, all right. Let's go to the last one, tangent. I tried to make tangent kind of easier because I know tangent's kind of a pain anyways, because it starts right over the origin. So I didn't want to shift it right and left. That causes issues, I know. So I just left it where it was. The period length for tangent is normally pi. So I divide it by the number in front of x, so it's pi over 3. Half of it goes over here. Half of it goes over here. So it's pi over 6. Pi over 6 is half of pi over 3. Then you cut it in half, cut it in half. The outside have asymptotes, and tangent starts in the upper right corner, goes to the bottom left. It hits the major markers. The markers are something I noticed people got wrong. It was shifted up 7. You have to go up 6 and down 6 from there. I had somebody tell me that 7 plus 6 was 12 or 11 or some goofy number. Okay, all right. Let's go down to the next one. Okay, number 4. Okay. You have to factor the top to figure out x-intercepts. When I factor the top, to the 18, that was 9 and 2, negative 2 I should say. So I was going to hit negative 9 and positive 2 for my x-intercepts. Now, for the y-intercept, you plug in zeros to everything, and it would have been negative 18 over negative 18, which is 1.
I got it right.
And then the asymptotes, since the top and bottom are the exact same powers, I believe. Are they the same, or is that bottom one 3?
Yeah, same.
They're the same, so you divide 1 over 2, so it's going to be a half. And so the tails will go to half, and then this middle was kind of going through. The most common mistake people made was putting this graph in the wrong corner. I couldn't hit the x-axis over here, because the vertical asymptotes were at 3 and negative 3. So I had to have those in there, and so I had to be up here because I couldn't hit the x-axis, and I had to be down here because I did actually hit the x-axis once. I just had some goofy answers where people were putting some curves. I didn't count them wrong necessarily because you were going off the data you knew. So I want to see, were you hitting the right axes? Were you hitting the right, X and Y intercepts? Were you doing the vertical asymptotes in the right spots? Did you have enough graphs in the whole thing? That's usually what it came down to. Did it flatten at half? A lot of people forgot to divide the leading coefficients because the powers turn out to be the same. All right, let's go to the next page. So second page now. Number 5 is almost the exact same. Now, on number 5, the power on the bottom is actually larger than the power on the top. So that means it's going to flatten at 0. That's where the end behavior goes. Because if the power on the bottom is bigger, it will flatten out at 0. So that's where you're seeing that little horizontal going across. Symmetry, it's not, so you can see it. X-intercepts have a factor at the top. It was -4, -2. I just drew that curve like that. That's where I'm assuming, because there is vertical asymptotes at 3 spots. There's a vertical at -5, there's a vertical at 0, and a vertical at 3. And because those are how I factored the bottom. Yes, there is a 0 because the X is outside, so there was a 0 there and it didn't matter that it was squared. It's still an asymptote of 0. So then at this point, when I draw my little items in there, I just had to make sure that I had 4 graphs. That was really hard to see. I put 4 graphs. I just kind of threw them in there. I just need to make sure I'm hitting the x-axis in certain locations. You could have had a different looking graph completely. I'm just throwing them in there where I think they should go. It could have been the opposite direction. Some people had some pretty wild graphs just because you had to have 4 pictures because there's 3 vertical asymptotes. It had to balance out at 0. That's really the little things I was checking for. There is no y-intercept on this problem because when you plug in zeros, you'll get 8 over 0, which is an issue. So that's why there's no y-intercept here. Question.
Or since you've already graded them, I'm going to let you in on a secret. I forgot to check if there was y-intercepts, and I drew a random horizontal asymptote in there.
Yeah. Okay. All right, number 6.
I made a slant going this
Oh,
way.
you're so lucky I didn't catch that. Oh my god, it must have been really faded. All right, number 6. Oh my god. All right, number 6. Okay, all right. A, B, C, D, E, F. All right, now, the limit, as I approach -2 from both sides, as I approach -2 on the x-axis from both sides, it's around 4 or -3 or 5-ish. Wherever you think that is, I thought it was about 4. You had to be in the ballpark. If you said 3 or 5, I probably crossed out and I said okay. Because you were in the ballpark. I'm not going to count it wrong when you had to interpret it. If you were way off, I probably counted it wrong.
But I think D&E was kind of close.
Definitely not. It actually went to a number. Now, next one. As I approach 0 from the right and left, it's going to hit 7. That's where the graph is approaching 7. I know there's an open dot there. It still looks like it's approaching 7, so that's what the limit would be. Now, number 2 from the right and left, that doesn't exist. They're going to 2 different numbers from the right and left side when I approach 2 on the x-axis. That's the one that doesn't exist because you're going to 2 different numbers. Now, as I approach 4, from the right and left, it's getting closer and closer to 8. So that's 8. As I approach 2 from the right side, that's going to hit 2. And as I approach 2 from the left side, it is approaching 3. That explains why letter C was a do not exist. Those 2 were not.
That I changed it.
Okay, all right.
It hates you.
Now, 7.
Every single one.
Ward, you hate me.
Yeah.
Are you sure?
With a passion.
This grade says different.
Oh,
Not my fault.
Oh no! I haven't started.
All right, number 7.
Not hard enough.
Okay, number 7. All right, now, what this is actually asking, if you do the limit, if you divide these, I'm actually asking where the horizontal asymptote is. Because as you go to the left or right, this one's asking you to go to the left, -infinity. As you go to the left, you are just figuring out where the horizontal is going. Well, the bottom power is too large. It was x to the 6th. So if the bottom power is bigger, that means your horizontals will be at 0.
oh,
And that's where the limits will be. That's where the tails will end up going. If I go further and further to the left, they'll balance out at 0. Now, if the top and bottom are the same power, that means you're going to go to whatever the leading coefficients divide out to be. 20 divided by 40 is half. It's half. And that's where the horizontal is. In fact, it's almost the exact same problem I did on the earlier problem. Number 5 or 6 or whatever that one was. 5 or 4, I guess. All right. So, if you're going to retake, it'll be a new test, new pictures. It It won't be any easier, any harder. It's just be different. I'll just throw different numbers in there, a different graph. If you choose to retake, it's got to be done by Thursday this week. You can always review, but I'm going to take these back. They're going to go in right before you leave here today. I'm going to enter them in. All I want to do today is intro what we're going to next, and then we're done for the day.
I didn't lose that. I got paramedic. I like to hear me back.
You do not have to buy hold of the desk.
If they break, I got yelled at last time somebody broke up my chairs. I don't know how I get yelled at for the stupidity of somebody else.
See the sucker?
At Kevin Myers.
Don't you get a week ago? Yeah.
My bad. I'll retake it. I'll be more specific.
What do you mean when I retake it?
What'd you get?
I'm not retaking it.
Travis, what did you get?
What did you get?
Not him. Lower than that, higher than Ryan.
You think I'm retaking?
I think I got like
68.
You think I'm retaking a lucky score like that?
Give him the glass, though.
I couldn't do that again in my
Or you should put mine in right now so I
Well, say you're
know
gonna
if I want to retake
Okay.
it.
All right.
Or when you're done with it.
Okay, first of all, have your notes up real quick. I want to talk about a quick idea of what we're going to be covering these next couple days here. So you need to have your notes out, please. Have your notes out. All right. Okay. All right, so again, what we're doing today, we're just going to do a quick review of...
What's this chapter called?
Okay, this section's based on derivatives, so it's, I believe they call the slope of lines. So,
Derivative.
so that's what we're going to talk about right now. So good question. All right, so we're in section 5.1. This section, or the chapter is based on derivatives.
What's the hardest chapter we're gonna do? This is the chapter name, not the section.
Chapter name is derivatives. The section we're in is slope.
I spelled it wrong.
Ward, can I go get my notebook?
Yes, right. Okay, so we're going to be based on slope. Now, the good news is we've already done a little bit of this before. Slope. It's called the average rate of change. That is what slope is. The average rate of change.
Is this physics?
Yes, very, very close. We're going to be doing this stuff very, very similar to physics.
Yeah,
very, very differently. Yes. All right. So now, what rates of change are? It's based on y-axis and x-axis changes. It is a ratio.
I'm using it.
The ratio that we know that you guys have been taught since Algebra 1, it was delta y over delta x's,
I have not.
which means rise over run. That's what they teach you in Algebra 1. It's a change in y's, which means delta, which is y minus y over x minus x. That's an average. Okay, it is basically if you had a curve or a straight line or whatever you have, it is looking at the straight line that connects it. So like for instance, if you were going to have this curve that kind of gently increases like that, the curve is increasing as we go, right? We can look at any 2 points we want and find the slope between them, right? It's this idea that the slope is that dashed line that would connect straight to them. Okay, that's slope. That's an average. It's not perfectly exact. Now, what derivatives or slopes do for us, it helps us find that rate, that instantaneous rate at a curve. So for like instance, a civil engineer, when you go north of Gardner, you go past Quick Trip, right? They have that Quick Star, whatever they call it. All right, you have that little curved road, right?
Yeah.
That curved road, they say it's like 25 miles an hour or 35 or whatever it is. Okay, yeah. So I know everyone goes different speeds. Now,
Can you set up like a thing on your GoPro to make it last longer on the battery? Like a time lapse?
yeah. I mean, I can do it where I can change the quality down because right now I'm just cooking. I'm recording in 4K and stuff like that.
Have you ever hacked something?
What are you talking about?
Like hacking something? I don't know. I don't think you can legally say say this on camera. The cameras are on.
All right, now. Okay. All right. So let's talk about some basics things here. So what a civil engineer does is they look at, when you're on a curve, they look at the instantaneous rate of change of that curve. What is the slope at that very moment? That is the speed that they rate it at. Now, when they say 25 miles an hour, it's an average, right? It's not any specific science. They've rated that curve. They've rated that curve at some type of weight of a vehicle, some type of tire that's on the vehicle, super generic numbers. Yeah, I understand. Your car can probably go faster on that curve. I'm not recommending. I'm just saying that some civil engineer has come up with an average between all the vehicles, all their weights, all their center of gravities, and said, this is the optimum speed for you to stay on the curve and not to break traction, friction, and to continue off the curve using inertia, right? This speed right here, this is called instantaneous. That is not what we're doing. We're not finding the instant speed on the curve. We're finding an average like that, where you pick 2 points and said, okay, I'm going from here to here, and I want to find that average slope between them. That's what it can give you. It can help you find the speed you can travel. And if you go closer and closer to the edge, that would become an instantaneous velocity. So now you can tell what the speed of somebody is actually on the curve. So that's something that they use. So like when cars when planes are up in the air and they're trying to take your speed. That happens all the time in this area. They have a certain plane that flies overhead, tracks speeds of vehicles, they call it in. They look between certain telephone poles to see how far you're traveling. If you're on a curve, they'll find an average between your speed. They'll look at 2 points on the curve and say how much time elapsed, and they can do a quick calculation. Okay, he's averaging about 50, 60, so he's speeding on that curve. That type of thing. They just do it really quick, and they don't do any of the math that we're going to do. They just have a simple formula. They plug the numbers in, it spits out on the calculator. They don't have to think about it, and they can call in wherever they need. We're just looking at the basics. We're looking at how do we find these numbers. Now, obviously, we're going to be finding way, way, way better ideas of how to do this. If you think back to Algebra 1 days, this is how they teach you. These are this. That's how you find a slope. We have a different way of finding slope. In pre-calc, to find slope of anything, including curves, this is the formula we have. It's called the differential quotient.
Oh, no.
We're going to practice some of that. Then we're going to learn shortcuts. Because, what was that?
This was with Stein.
Yeah. We're gonna do that because we're gonna start with this easy stuff. Then we're gonna work a little more difficult. Then we're gonna get to the part where we're doing some serious slope and derivatives and other things. Derivative again is a type of slope. It's an instantaneous
Have you
slope.
talked to him lately?
And the idea is that what we're gonna be looking at is finding derivatives for any type of curve at any moment, and that's what we're gonna be learning over this unit. Does that make sense? Okay, let's do one example, then we're done for the day. One example.
I
Okay.
can submit my score, right?
All right, here we go. One example. Let's pick this point right here, and let's pick this point down the road. All right. So, this coordinate here, that was what, 3, 2. This dot right here was 1, 2, 3, 4, 5. So -5, -1. All right. So, to find the average slope between those two dots, you plug them into here. What are my y numbers up there? 2 and -1. I don't care the order you put it in, as long as you have to subtract whatever the two numbers are.
3 over...
So now, when you pick that route, so I pick the back and the front. I have to stick with that from now on. So now I have to go 3 minus the -5 route. Once you pick the top one, that tells you the direction you have to head. Back minus the front. Maybe you went front minus back, doesn't matter. So this ends up being 3 over 8. That is your average rate of change. That is the rise and run. I would rise 3, run 8.
Can't you just count it?
Yeah, I mean, in theory, yeah. If you have it, you can just count with your fingers to know slope for equations of lines.
Are we gonna have any funky ones?
Curves, that's what we're eventually going to be getting to.
So that's why we need the differential.
Yeah, the differential quotient or the shortcuts we're going to be learning throughout this chapter will give us the slope for anything
I say
at
we
any
just
moment.
that
Could you
one.
throw up the differentiation thing on the board again? I was gonna write it down, but I don't remember.
Yep, I'm gonna do it just for a generic problem. So,
That's
something
actually-
easy for right now, and then we'll do more difficult ones tomorrow.
F equals X times.
Okay. Okay, all right, so let's look at the differential quotient. Let's do it for, let's do this. Y equals 4x minus 1. Let's say that that's my function, right? This is my f of x. F of x means y. It's the same thing, right?
Yep.
And so if I do the differential quotient, this is the formula that they teach you, okay? Okay, that's the formula that they have. This just shows you how to plug in your equation into that, and it will give you the average rate of change. Okay? So what you do is you take your function and you plug in x plus h into the entire thing. Wherever there's x's, you'll plug in x plus h. So that's this upper left corner. So my function with x plus h's plugged in. Does that make sense? That's the original function. Wherever there's x's, x plus h has to go in there. Now, I have to also subtract the original function off of it. So I'm going to subtract, in parentheses, 4x minus 1.
What's be plus over H?
And then this is all over h. And the h goes on the bottom.
Wouldn't it be plus 1?
Eventually, yes. Because we'll distribute the negative sign, right? Okay, does that make sense to the setup? Pick your function, x plus h's are plugged in, you subtract the original, all over h, we simplify. So, we distribute the 4, so that's 4x plus 4h, the minus 1. We distribute this negative sign to the back, to everything, so that's negative 4x plus 1. And this is all over h. Here's how you know you do it right. Here's how you know you did it right. Everything without an h will cancel out. So, everything that doesn't have an h should go away. And that did actually happen. And so what we're left with is this. The h's will divide. And what you're looking at here, this is the average rate of change over the life of that function, which makes sense because the slope of that function was 4. That's what the differential quotient tells me. So on a line, that's really easy. We already know the slope going into that line. This formula spits it out. It spits out that this formula should have been 4. If you have coordinates, fine. You do the old school subtract y, subtract x's. What we're going to be looking at is curves. And that's the stuff that I think Stein went through with you, where you have really complicated functions where they're actually like curves.
Yeah, so I
And we're looking for the differential quotient at any moment on the curve. That gets challenging. That's where this formula gets really messy because you're foiling and distributing and doing weird stuff with powers and stuff. And things cancel and then we have to learn little steps. That's what we're going to be doing the next couple days. Make sense?
Yes.
Okay. That's it for today. So pretty easy. I'm going to enter some scores for you guys.
Or let me know when you submit it.